Hello everyone, welcome to OneClass. My name is Shanjida and today I'll be going over some commonly asked math questions, chemistry questions, both at the high school / university and college levels. If anyone needs additional schoolwork help or needs tutoring, you guys could check out the description box below. And lastly, I am currently a second year human biology student studying at U of T. So without further ado, we could get started. And so the first question here says what intermolecular forces are present in NH3. So NH3, this is ammonium. Okay, so we're trying to find out the intermolecular forces that are present in NH3 and the two main forces that are involved. Okay, there are two main intermolecular forces. Intermolecular forces involved. Which are hydrogen bonding and your dispersion. And dispersion forces. So we'll go over all of them one by one. But however, intermolecular forces are forces that hold the molecules together in a solid or a liquid, which is stated here. And so these forces are generally much weaker than intramolecular forces, and those are forces that hold atoms. So like the main compartments of the compounds together to form molecules. And so the strength of intramolecular forces is directly proportional to the polarity of the bonds. So we can say the strength of inter of intermolecular forces. This is directly proportional to the polarity of the bonds. Okay, and so what we mean by this is that as the bonds become more polarized, the charges on the atoms become greater, so we can basically say as bonds become more polarized, the greater so the greater intermolecular and so when we're talking about intermolecular forces, there are four main types, or four major classes. or major types of of um of interactions, intermolecular force. So these are the number one, which is the strongest. This is your ionic force. Okay, and so this is when it is between. So this force is made when it is between a charged atom or molecules called ions. So made by charged atoms, also known as ions. Okay. So the highly polarized or charged nature of the ionic molecules make the ionic bonds the strongest among all the intermolecular forces. So this is so basically your atoms are highly polarized. Okay, and so this makes it the strongest. Strongest force um, be, of the of between or among all the intermolecular forces. So the second one we have is called hydrogen bonding. One main type, this is formed between a nonmetal and a metal. Okay. And so for hydrogen bonding, this occurs in molecules containing highly electronegative elements. Okay. Like chlorine, nitrogen, and oxygen. So these are directly bonded to a hydrogen. Okay. Although the bonds possess covalent characters, right? So you know that fluorine, nitrogen, and oxygens are all nonmetals, so they possess covalent bonds. The difference between the electronegativities of the atoms and hydrogen bonds makes the molecule partially positive and partially negative. So you have positive and negative um charges on opposite sides. So we're rating the forces from most strongest, going from most to least. And so you can say that hydrogen is the second form of strong intermolecular force. So our third would be dipole-dipole interactions. Dipole-dipole interaction. These are other elements besides um besides hydrogen, and so basically they form that form bonds with bonds with another element. Another element, basically, with another element with different electronegativity. And this creates these dipole-dipole forces. So this creates a dipole-dipole. And so the electronegativity difference also creates partial charges on different sides of the molecule. So you say we have also have also have partial charges. And lastly, the weakest one is London dispersion forces. London dispersion. Okay, so this is the weakest. So weakest intermolecular force. However, the strength of these forces generally increases. So they increase if the total number of electrons also increase. So normally, all compounds have London dispersion forces, all of them. And so, since it's the weakest, we increase the bonds of London or increase the force. If you have a lot of forces, it would become really strong. Okay. And in this problem, it is asked what are the intermolecular forces um, of ammonia. So it is hydrogen bond because there's a presence. So we can say 4 NH3. We have hydrogen bonding. Okay, we have hydrogen bonding because we know that hydrogen bonds with because hydrogen bonds with fluorine, nitrogen, and oxygen. Okay, so it has hydrogen bondings, which also has a large difference between the electronegativities. So which also has a large difference, um, making the molecule polar. So it's making the molecule polar, creating partial negative side and a partial positive side. And so, so we have both that. Um, so however, when other molecules interact with it, the partial negative, which is the hydrogen, will bond with the partial positive of the other molecule. Sorry, so the partial negative would be on the nitrogen and partial positive would be hydrogen. And so that's how it would interact, and that's how it creates the hydrogen bond. Okay, and so We also have London dispersion forces. So as I mentioned that because they are present in all molecules. Okay. Um, because they may form between hydrogen interactions or two different molecules of NH3. Okay, so these are the two main forces or the only two forces, intramolecular forces of ammonia. Okay, so we have hydrogen bonding and dispersion forces. This is our second question. Guys, what is the pH? So what is the pH for a 0.35 molar aqueous solution for sodium formate? I'll just write given. That's what we know. We know that the concentration of sodium formate, which is NaCH02, is 0.35, right? And we know that the Ka for formic acid is 1.8 times 10 to the power -4. And so we're trying to find pH. Okay? And so what we have to do here is basically we have to basically measure or first come up with an equation for our acid ionization constant, right? So in this case, since we're talking about acids, we're dealing with Ka, and this is the equilibrium constant for chemical reactions involving weak acids and aqueous solution. And so for this, or for generally how Ka is expressed is Ka is equal to the concentration of your H plus ions and your conjugate base or your conjugate acid, and over the reactant for your acid. Okay, and so where, as I mentioned, that H plus your concentration of hydrogen and the concentration of your A minus are the dissociated ions. And so meanwhile, if we're talking about Kb, just general, Kb is used for bases. And this is where to measure how completely a base dissociates into its component ions in water. And so the formula for Kb, as you can probably guess, is B plus. So this is base. And this would be your OH ions. And all over your base. Okay. And so how we can relate Ka and Kb is by this expression. So Ka and Kb are related to each other through the ion constant for water, Kw. So Kw or Ka and Kb are related by the ion constant of water. Okay, and so this is Kw, which is for water. Kw is equal to Ka times Kb, and this value, okay, so this is actually equal. This is equal to 1.8 times 10 to the power -4. Okay. So this is constant. The ion constant of water, your Kw for water is always constant, which is 1.8 times 10 to the power -4. And so in this problem, the value of Ka of formic acid, or sorry, it's not 1.8, sorry, it's going to be 1.0 Kw so the value for Kw is 1.0 times 10 to the power negative. So it's -14. Okay. And so what we can do is we can basically, since we're given the Ka for formic acid, we can use this, we can use our Ka expression over here and substitute what we know. And so let's say, so let's write out the equation for, so the reaction for formic acid, which is HCHO2. Okay, and so this is dissociate into its ions, which is H plus, and you have CHO2 negative. Okay. And so we want to express this as Ka. What we would do, we would say Ka is equal to, so the products, which is H plus times CHO2, and your acid, which is HCHO2, right? And so Ka in this case, since we're given Ka, which is 1.8 times 10 to the -4, so we can substitute 1.8 times 10 to the -4 for Ka, and we get, so this is equal to H plus and CHO2 negative all over HCHO2. Okay, and so since we expressed this, but the solution in the question is the aqueous solution of sodium formate, which can be, so we have to basically find sodium formate is a base. And so what we need to do, come up with an equation where sodium formate reacts with water and produces its ions. So we have NaCH O2 reacts with water. Reacts with water. And we have this equilibrium equation. We have O2 plus NaOH. And so from the equation, the value of Kb can be expressed. So since we're just interested in the base, right, and the ions, and in this case, we would have, so since water would not be included in our Kb because it's liquid, right, we want aqueous solution. Kb would be HCHO2 into our own. So we're just interested in our hydroxide ions, not sodium hydroxide. And this would all be under CHO. Okay, we're not interested in the sodium, we just want the ion. And so back to our Kw expression, right? We can now basically multiply Ka and Kb to get our final acid dissociation, or our water dissociation constant, right? So Kw, as you guys know, is K times A, Ka times Kb. And so let's multiply these two out. So from our Ka, if you recall, we have CHO2 negative times H plus all over H CHO2. And so we're going to multiply this with our Kb. We have H CHO2 times OH all over CHO2. Okay? So we can see if we multiply this, we can cancel out this, and this. And so what we're left with is our H plus concentration times our OH one. And this is what your KW should give you. Okay. And so we can basically say that KW is equal to concentration of H plus and OH. And so it is known that the product of the concentration of your hydrogen ions and your hydroxide ions in any solution, this is equal to 1.0 times 10 to the power negative 14. Okay. And so from this, knowing this, we can now find the actual the KB value, your base dissociation constant. And so we can basically now rearrange this equation where KW is equal to Ka times Kb. Rearrange this equation to find Kb, so we have Kb is equal to Kw over Ka. And we know what Kw is, which is 1.0 times 10 to the power negative 14. And Ka is given, which is 1.8 times 10 to the power negative 4. So then our Kb is 5.5556 times 10 to the power negative 11 for Kb. So since we found Kb, we can now basically, so this is equal to our expression, right? Our Kb expression. And so what we have to do next, we have to create an ice table. I'll just rewrite the equation. So for how our sodium formate dissociates when it reacts with ionizes in water. So we have NaCHO2 plus H2O is an equilibrium. And so this will react. So this will be a form of HCHO2 plus NaOH. And so what we're going to do is form an ice table. So we have ICE. So we're going to first put our or have our reactant, which in this case is sodium formate. So let's say we have in this case sodium formate, and then we have our products, which is CH, HCHO2 and OH negative. So we're just going to put in the known concentration, our initial concentration, which is 0.35. So 0.35, right? And our change is going to be negative X because we are completely dissociating sodium formate into their ions. And so this would be 0, 0 plus X, and you have 0.35 minus X. You have X here and X here. Okay. And so what we can do, we can now apply the concentration. So we can basically say that we can basically write this as our Kb expression, where our Kb was equal to 5.5556 times 10 to the power negative 11 is equal to our Kb expression, which was, we're just going to substitute what we know. So since our Kb over here was our products over our reactants, so what we're going to do is substitute what we know. So on the top, we would have X and X, right, from this, and right, our denominator would be 0.35 minus X. Okay, and so solving for X, which is also the value of the concentration of OH, or hydroxide ions, in the equilibrium state of reaction. So if we rearrange this equation, basically squared 0.35 in this case, you can basically cancel out the X here. And what we have is you would 6 10 to the power negative 11, and you would multiply this with 0.35. We're just rearranging, so we solve for X. Right, and this will equal to X squared, and so X is equal to the square root of 5.556 times 10 to the power negative 11 times 0.35, right? And so once you do this, that X is equal to 4.41 times 10 to the power negative 6. Okay, and so this is also equal to the concentration of your hydroxide ion. Okay. And so now pH can be calculated. As you guys know, when we're dealing with bases, they're gonna take into account of pOH, so the pH of your base. And so this would be the first step, and this is negative log the concentration of your OH ion. And so this would be equal to the negative log of 4.41 times 1 times 10 to the power of negative 6. Okay, and so what you would do, so once you evaluate this, you get 5.3556. And since we're trying to find pH, you guys recall to find pH from pOH, we have to use, since pH plus pOH equal to 14. To find pH, we can rearrange the equation and you get 14. You have 14 minus pOH, right? And so you have pH equal to 14 minus 5.356, and pH is equal to 8.644. Okay, this makes sense since this is a base, right? So your pH would be above 7, and in this case it is. And so let's see. So it's given the pH of the solution is 8.644, and so the solution here is correct. Okay, so our next question says, what is hydronitric acid? So hydronitric acid is a weak acid, and it is soluble in water and it forms acid salts. So its chemical formula is an HN3. So from the name hydronitric acid, right? So you can imagine that from the name it has hydrogen and nitrogen. So nitric is something that's H3, and if it's hydro, that means it's only has one hydrogen. So in this case, it would be H. And it is a weak acid and it forms acid salts. Okay, so weak acid. So this is okay. So our question here says, how do you calculate the average atomic mass of magnesium given the following percent abundances and isotopic masses? So we're trying to find the average atomic mass of magnesium, and to calculate the average atomic mass, the percent abundance is basically multiplied to the isotopic mass, and so the average atomic mass of magnesium based on the given problem, so what we're going to do is multiply the percentage with the atomic mass given for each of the isotopes that magnesium is found. And so we can basically say, so 78.99%. So we have to convert that into a decimal. So we divide that by 100. So we have 78.99 divided by 100. And you get 0.7899. Multiply this with 23.985.8504. Okay. And once you multiply it, you get 18.945783, which is the atomic mass. Okay. And so for the second one, you have 10%, so you do 10 divided by 100, you get 0.110, right? And you times this with 24.98584. Okay, and you would get 2.4 times 0.4 98584. That's your atomic mass. And lastly, you have 11%. So 11 0.01% over 100. And this is equal to 0.1101, and you multiply this with the atomic mass, which is 25.98259. Okay, and so once you multiply this out, you would get 2.86068315 mass. And so the last step would be to add all this up to get your average atomic mass. Okay, so we say add so we have 18.9457.831 plus 2.498584 584 plus which is 2.860683159 3159. And so once you add these two numbers together, you would have, so you add all this together and you would have 24.30505026 as your atomic mass. So this is your average atomic mass of. Okay, so let me see. Okay. The next question says, how do you determine pH from molarity? So, as you guys know, that pH is a measure of how acidic or basic a substance is, right? So, if you have pH scale right here, so 7 is your middle point, and this is neutral. You have 14, and so this is your basic side, and this is your acidic. Okay. And so this is a scale of to measure how acidic or basic a substance is. This is 37, 7 to 14. And so as pH approaches 0, the acidity strength increases, while as the value approaches 14, so to the right-hand side, the substance becomes more and more basic. And so molarity or molar concentration is the number of moles. So if we say, let's write molarity. Molarity is the ratio of the number of moles of the solute by the kilogram of salt. Oops. Molarity is the number of salt. I was thinking about molality. Molarity is the number of moles of solute per liter of solution. So liter is okay. And then it can be calculated by like this formula. And so concentration is also known as molarity. And so you can say this is equal to concentration. And so concentration also can, so this can be used to determine pH. So for example, let's assume, let's say, for example, let's say we have a sample of nitric acid that has a molarity of or a concentration. So of nitric acid, which is HNO3, this has a concentration of 0.0032 molars. Okay, and since HNO3, nitric acid, is a strong acid, it will completely dissociate into hydrogen ions and nitrate ions, or nitric acid ions, and so the molarity becomes the concentration of, so you can say since is a strong acid, since HNO3 is a strong acid, the concentration of H plus, or so it could completely dissociate into their individual ions, which is H plus and your nitric ions. Okay, and so this means that, so you can say the concentration of your H plus ions equals to the concentration of your nitric acid, which is equal to 0.003. Okay, and now to find pH, there's a formula for this where pH is calculated by the negative log of the concentration of your hydrogen ions. Okay, and so you substitute the value of 0.0032 into this. So you have negative log of 0.0032, and you would get a pH. If you put this in your calculator, you get 2.49. You can see this is very acidic since it has a pH of 2.49, and this is how you find pH from molarity or concentration. So they've given the formula for molarity, and concentration is basically molarity, and if we use to determine pH, this is what we just done here, and the solution is correct. Okay, so our next question says, give the IUPAC name for each of the following carboxylic acids. Okay, so simple carboxylic acids derived from open chain alkanes are systematically named by replacing the terminal E with an alkane of the corresponding alkane name with an oic acid. So the branch carbon atom is numbered as carbon 1. And so compounds that have C double bonded O group bonded to a ring are named using the suffix carboxylic acid, and the C double bonded O carbon is attached to the carbon 1 and in this system, and is not itself numbered. So as a substituent, the C double bonded O and an OH group is called the carboxylic group. So what I mean by this is that there's C double bond. So what I mean by this is your C double bonded OH is this is called a carboxylic group, carboxyl group. Okay. And so we're given 4 compounds here, and we're supposed to find the IUPAC name. So let's first draw them out. And so A, H, O, H, double bonded O, double bonded O, right? And in this case, we can name the or like number the carbons. So let's say this is 1, 2, 3 carbons. And so you can see we have 3 carbons. So this would be a prope, propane, because it doesn't have so like the carbons are not double bonded to each other. And so since it says since we have 2 carboxylic acids, so it would be di, and it says to replace the terminal E with an oic acid. So this would be, so therefore we have prop and dioic acid. And B, so B, we have so this big carbon chain. So we H O double bonded at O, CH2, H2, CH, CH3, and this is bond with another CH2, and this C double bonded O with the O2, with an OH, right? And so we can name this off by naming off our carbons here. So 1, 2, 3, 4, 5. So our longest chain, right? And so we can first name it off, how we name it off. So like we have a methyl substituent, right? And we have 2 carboxylic acids. So our name would be 3. So it's on the 3. So on the 3rd carbon we have a methyl. So it's going to be 3-methyl pent, right? We have 5 carbons, pent, dioic, since we have 2 carboxylic acids, dioic acid. This is for B. And now let's do C. C, which is this molecule. COOH and our C. And okay, so let's first let's count off our carbons. We have 1, 4, 1, 4. Let's go 1, 2, 3, 4, 6. Right, we have 6 carbons, and so our substituent over here is chlorine. So our name for this compound would be 2-chloro. So since it's 6, it's a benzene ring, right? So it's going to be chlorobenzoic. So in this case, notice that it's not di because we don't have 2. carboxylic acids, it's just one, so it's going to be benzoic acid. Okay, so that was for C. And now for D, we have this pentene ring. Okay, and COOH, and we have a point. Okay, so let's name our carbons. So we have 1, 2, 3, 4, 5. And how I would name this? So we would name this by first naming our substituents. In this case, we have chlorine, so it's going to be 2 oral cyclo, right? So cyclopentene, because it's in the cyclic form, cyclopentene. Pentanoic acid. So since it's cyclopentane, we can also say this is as one carboxylic acid. Carboxylic acid. Okay, since it's cycle, so we can say that this is carboxylic acid, 1 carboxylic acid, or we can also say this is a pentanoic acid. Okay, so and so these are the 4 compounds and the names. And so yeah, for D, I would just say it could be 2-chloro-cyclo and so the solution is correct. And so basically that was the end of our session. If you guys like this Q&A, please subscribe to the OneClass channel. And if anyone has additional questions they want to ask, or like personal questions about any type of from any of the subjects, and you guys could check the description box below to ask your questions. And if anyone needs one-on-one tutoring services, you guys could also check the description box below. Other than that, I'm Shanjida, and I hope to see you guys soon. Bye bye.